Yeah, before we begin today, let me answer a question that was raised which had to do with ergodic sampling and ergodicity. The statement made was that if you have a time average, you could in principle convert it to an ensemble average if you have ergodicity in the system, and this is used in practice in sampling, in experiments, in physical practice. It is used all the time, and let me give an analogy for this. Suppose we wanted to measure, we have a long roll of wire, homogeneous, uniform everywhere, and we wanted to measure the resistance of this wire, of 1 meter of this wire. There are two ways of doing this. One of them would be to say, I have available to me a single piece, a meter long, and I measure its resistance, and I do this over and over and over again, and each time I make this measurement under identical conditions, I get a slightly different answer due to various fluctuations, and I take the arithmetic average of all these measurements, and that would be the time average of this resistance, and it gives me a certain number. We are assuming here that this wire does not in any way change its characteristic due to these measurements. It does not become old, it does not get heated up, it does not get aged, and so on and so forth. The other way to do this, to measure, get an accurate value or average value for 1 meter long wire, would be to take this long spool of wire and make a measurement for each of those pieces. So the next piece is like this, and the next piece is like that, and so on, and I measure each one of these guys and ask what the average value is. This would be like an ensemble average. An ensemble just means a collection, a whole set of these identical copies, and it is again assumed that these pieces are all identical to each other, and that gives me one average value, and that may not always be practical to do. You may have available just 1 meter and no more, in which case to get an accurate value you would repeatedly measure the same thing under hopefully identical conditions, and then assume that the time average that you get by measuring the resistance of 1 meter of wire, a single specimen over and over again, is the same as the ensemble average. So this would be an illustration of ergodicity, in the sense that you have replaced a time average by an ensemble average. Now what is implied in this whole business in some sense? What is implied is that there are certain sources of fluctuations which lead to an answer which is slightly different each time when you make this measurement over and over again. Some random processes are operating, internal, external, we do not care, such that there are fluctuations in the answer when you make this measurement here. The assumption is that the system, as time goes along, runs through all the realizations of that random process which is leading to the fluctuations, which would otherwise be reflected by the small differences in the different samples. In other words, whatever fluctuations are going on in time here, that is already captured at the same instant of time in the different parts, in the different copies or members of the ensemble, which is why you equate the two. And in dynamical systems, as you can see, when a system is ergodic, it says instead of computing time averages, a long time average over a trajectory, at a given instant of time I compute a phase space average over different portions of phase space with some given measure, and that is again the same ergodicity. So it is precisely the same thing that is being done in both places, and the hope is that under suitable conditions the random process or whatever else is determining the fluctuations here is such that a time average could be replaced by an ensemble average, and this is at the root of all ergodicity. Yeah.
Ergodicity can be used when, like, you know that the system is ergodic and so you can replace.
Yes,
so,
absolutely.
Is there any way by which you can find out if the system is ergodic without actually verifying the time?
Yeah, this is a good question, it is a deep question. How do we know a given system is ergodic? First of all, you have to specify a system much more accurately to do this. Given a dynamical system, given the rules of evolution, in our context we can certainly test if a system is ergodic or not. We can run a typical trajectory through, or we can use other criteria for ergodicity. If we know something about the dynamics, if we know something in detail about whether it is expanding in one direction, contracting in another, and so on, we may be able to prove ergodicity in a rigorous sense of the word. But in practice, coming to this experimental question of,
you can prove ergodicity without having an explicit equation for the time and
No, I am assuming that we have a dynamical system for which the equations are given to you, the dynamical system.
Explicit solutions in terms of time.
Without an explicit solution, yes.
There is a point in having
Yes, oh yes, you can still do that, yeah. You don't need to be able to solve this system completely. You can still prove that it's ergodic. You can still show that it's ergodic. You don't necessarily need to solve the equations explicitly. In fact, in most cases I can't solve things explicitly. So that's not the problem. Proving ergodicity for a given difficult, complicated dynamical system is not a trivial matter, but it can be done in principle in most cases. On the other hand, yeah.
What are the things by which you can, what is the rule by which you can approach it? Because the only thing I told now is that these two are equal.
Okay, the next question is how do I know? How do I do this? This is going to involve something called coarse graining in phase space, and then looking at what happens as the system visits different parts of phase space. I will talk a little more about it a little later. So it involves other criteria, other quantifiers for ergodic behavior which we haven't yet considered, such as I break up the phase space into cells, sufficiently small cells, and keep track of where a representative point is. I can do that numerically without actually solving the equations of motion, and then depending on the statistics of how different parts of the phase space are visited and filled up, I can decide whether the system is ergodic or not. I can see what the dependence of various visits, of the statistics of recurrences to various cells and how they change, how this thing changes as a function of the cell size. That will give me another indication of whether the system is ergodic or not. So there are quantifiers for ergodicity. On the other hand, for a purely experimental question such as this, the resistance of a piece of wire which I am talking about, in practice it is clear you do not have a large copy, you do not have a very large sample, you certainly do not have 2 kilometers of wire to play with. If you did, then the ideal thing to do would be to cut it into 1 meter pieces and measure for each one of them what the resistance is and take the arithmetic average. Since you do not have that, you take it as an article of faith that whatever fluctuations occur in the remaining portions are all present in a given sample over a period of time, given enough time, and therefore you use just one sample but you repeatedly make measurements in order to find an average value, and then the hope is that these two averages are exactly the same thing if the system is ergodic, if it is ergodic. So this is the point of what it. In fact, when you do statistical mechanics or thermodynamics, you are using ergodicity essentially, because what is going on is that you put a macroscopic system under given experimental conditions, such as for instance in contact with a heat path in thermal fluctuations, a thermal equilibrium in contact with a heat bath, and then you assume that the system is ergodic. In other words, a statistical average over a given ensemble with a certain probability distribution is enough to give you long time averages for the system, because you can't follow the trajectories of a complicated set of interacting particles in time, but you assume that whatever information you would have got by doing the time average is already there when you do the ensemble average, and then it only remains to write down the correct measure, the correct probability distribution, and that is the task of equilibrium statistical mechanics. Okay. So once again you do precisely that. Now what is the reason why you are able to do this? Again, you do not have an infinite number of copies of an ideal gas in a container, although when you derive statistical mechanics or the rules of statistical mechanics, you assume, you pretend you do, and you have an infinite number of copies to take averages over, but a given system, a single system, the gas in this room for example, runs through all the realizations of the random processes involved given enough time. Okay. So this is the whole point. For instance, in different samples the molecules would be at different positions at the same instant of time, and the assumption is given enough time the molecules of a single specimen would run through and assume all those positions. So you certainly have to do an averaging for a sufficient amount of time that you think you have got a satisfactory enough long time average, which could then be compared with the ensemble average. Now since equilibration time in systems like this is very, very short, this is actually true in most cases in practice. Need not always be true if the relaxation times in the system are extremely small, then this is no longer true. If the system is extremely sluggish and there are time scales for equilibration or the running through of all the realizations which are much larger than the time scale on which you make measurements, then the system could get stuck in one or two preferred configurations, and then it is no longer a true average. This happens in many systems, it is called glassy dynamics. It again happens once again when you have extremely sluggish systems, systems with very complicated, what are called very complicated or rugged energy landscapes. So you do not have clear free energy minima, but you have minima on all, local minima on all scales, and then the system could get locally trapped in some place and take a long time to get out of it, and then of course it is not easy to take averages after that in such situations. So they do, these situations do occur in physics everywhere, but for us in the study of dynamical systems the equations themselves specify everything. So in principle that is all the information you have and everything has to be derived from there. Okay. So let us go back now and consider what one dimensional maps had to tell us. We looked at the logistic map, we looked at it at fully developed chaos, and we discovered that it had an invariant measure, an invariant density which was non-trivial and had a kind of square inverse square root shape. So for the logistic map at mu equal to 4, this was the map f of x equal to 4x times 1 minus x. We had fully developed chaos the Lyapunov exponent lambda was equal to log 2, the same as for the Bernoulli map, and the invariant density this was equal to 1 over pi square root of x times 1 minus x. Okay. So this is where we had got. Once you have this, then it is not hard to compute various physical quantities, because the average value of any function of x is simply its weighted average with this invariant density, and that is guaranteed to be the long time average. And of course you know that apart from a set of points of 0 measure, all points in the unit interval lie on chaotic orbits, and these orbits wander back and forth without settling down anywhere, and they fill up the interval according to this density which looks like this. Okay. Now there are certain universalities about this map which are common to all one-humped maps of the unit interval, and we will talk about some of these, but there is another phenomenon I would like to talk about today, and that is the phenomenon of intermittency. Intermittency comes in many varieties, and very roughly speaking it is the phenomenon by which a chaotic system displays periodic behavior in between, or apparently periodic behavior instead of being fully chaotic for long intervals of time, and then it is followed by bursts of chaos followed by bursts of laminarity, which is regular behavior of some kind or approximately periodic behavior. So if you look at the time series of any variable such as x, it would not show the truly chaotic up and down zigzag motion in an intermittent situation, it would actually show long bursts of periodic behavior, and then all of a sudden once again you have chaotic behavior. Now how does this phenomenon arise? Several routes to intermittency as I pointed out, but the simplest one of these is the following. Let me draw in pictures and show you what happens. Suppose you had a chaotic one dimensional map, here is the bisector, which looked like this, and this was the map function. It is easy to see that in this case you have a stable fixed point here and an unstable fixed point here where the slope is greater than 1. So if you start with points in between, they would end up at this point here. If you start at points here, it would end up at this stable fixed point. Now suppose you varied a parameter such that this map function, as the parameter varied, moves up, and there comes a stage when it's got a tangency at that place. So the slope is 1 at the point of tangency, and then as you varied the parameter further, the thing moves out and goes off like that. There may be other portions to this map function, but locally in the neighborhood of this point of tangency, suppose it looks like this as you tune a parameter, and I will give an example shortly. what would happen? And here is an example right away. Suppose you consider xn plus 1 equal to some constant mu plus xn squared, for instance, near the origin. So I have shifted this point to the origin and the map looks like that. What would happen? Well, clearly if you had the map near the origin, if mu is 0, dead 0, then it is xn plus xn squared and it looks exactly like this. There is a point of tangency with slope plus 1 and then it takes off like an xn squared. So this would correspond to mu equal to 0 and this would correspond to positive values of mu, but it is just moved off from there completely, and this would correspond to negative values of mu. So as you cross mu equal to 0 from left to right, the picture would go like this from here to there. Now at this place, in this situation there is no problem. This thing here is a stable fixed point, things get attracted to it. At this point you have something that is marginally indifferent, marginally slope is equal to 1, so the fixed point is marginal. Here as you come in here things would flow into this point, but if you started off on this side things would flow out. So you would have a behavior like this, in here it would go in, but if you started here things would get out. In this situation if I start here, I go to this function, I come here, I go here, I go take the staircase route and then I am off. As you can see, if this is infinitesimally close to this point, the bisector, there is a tunnel region where the system takes a long time to get out of this tunnel region and then eventually it does and does chaotic motion elsewhere, and then once it gets trapped in this region again for a long amount of time, there is again approximately regular behavior. It is not really going anywhere, it is stuck in this tunnel, and the moment it clears the tunnel it goes off and gets out and comes back. We can even estimate how long it would take to cross this tunnel behavior, this tunnel region, and this is type 1 intermittency, the simplest type of intermittency. We can easily estimate how long it would take to get out of this tunnel region as a function of this parameter mu, which is supposed to be infinitesimal here. So mu just a little bigger than 0, mu equal to 0, and this was mu less than 0. So let us look at this map here. Now it says xn plus 1 is mu plus xn squared. So it is clear that xn plus 1 minus xn is mu plus xn squared, and in this region the dynamics is essentially differential dynamics because it is making ever so small steps, and I can replace the difference equation by a differential equation in time, and it is clear this thing here is just the first derivative, so it looks like dx over dt is approximately mu plus x squared itself in this region, which I have drawn in a very exaggerated way. But the solution to that is obvious because it says square root of 1 over square root of mu tan inverse x over square root of mu is equal to t, assuming that I start near 0 at t equal to 0 and I move out, it is of this form here. So that immediately says that x is like square root of mu tan t root mu. In other words, to reach a point x to the right of the origin you need a time which is related to the space the x by this relation here. And what happens to this when t root mu hits pi over 2? It becomes infinite. So essentially it says that to cross this tunnel region the time of crossing t is of the order of 1 over square root of mu. That is the time it takes to get out of this tunnel region in an order of magnitude way. Now that is the reason why if mu is infinitesimal and you get closer and closer, it is going to take longer and longer. In other words, the laminar interruptions, the laminar regions in this chaotic time series are going to become longer and longer, and it looks like the system is not chaotic at all, but in reality it is, except that for long bursts of intervals of time you would see essentially periodic behavior or regular behavior. Now this kind of thing is seen in experiments in a variety of situations. In liquids, for instance, it is very well known that there are models of liquids, dynamics of liquids, fluid dynamics, this appears all the time. There are many other areas in semiconductor physics, chemical reactions and so on, where intermittency has been seen, different types of intermittency have been seen. The reason I said this is called type 1, let me mention this very briefly and perhaps we will come back to this a little later, is the slope at this point becomes 1, this is in marginal fixed point. But in higher dimensions, if you have maps in more than one dimension, then the marginality appears not when the slope hits 1 alone, but in the eigenvalue plane of the local Jacobian matrix. Every time eigenvalues cross the unit circle, you have this kind of behavior, you have marginality. And there are three ways in which eigenvalues can cross this unit circle. One of them is to cross the value 1, which is what happens here in a one dimensional map. They could also cross -1 in this direction, and then you have what is called type 3 intermittency, which perhaps I will come back to later, and then you could have a pair of eigenvalues crossing at complex conjugate points, and this will only happen in 2 or higher dimensional maps, and then you have what is called type 2 intermittency. We will try to come back to this when we do higher dimensional maps, but right now in one dimensional maps the slope crosses the value 1, and this is type 1 intermittency. And what you need to know is that this phenomenon is very common and it is part of chaotic dynamics, and the travel time through the tunnel region can increase scales like this parameter mu, like a 1 over square root of mu. Okay. Now let us try to study this in a little more detail and see what happens in a map which we perhaps could solve, and see the effect of this marginal fixed point. So let me do a map exhibiting yeah.
When mu is less than 0,
yeah.
near the stable fixed point there is no chaos, right?
There is no chaos, everything gets attracted there, yeah.
So what does this T as imaginary mean?
I said that the time that I evaluated was for mu greater than 0, the situation greater than 0. When it was less than 0 it just got stuck there, that is the end of it.
What is, you can still use it, right? If you assume in even that it was greater than 0.
What good will it do? I mean eventually things are going to fall into the fixed point, right? Whereas I am interested in finding out what the time scale or the way the intermittent regions scale as a function of the parameter in a chaotic situation, in a chaotic map. When you have a fixed point it just falls in, so it is not of great interest to me.
Shouldn't T be coming like infinity or something, because it's always there in the stable region?
In the stable region it will fall in, yeah. So that, oh, but that integral isn't true anymore, right? I mean this is not true. I mean dx over mu plus x squared is not equal to 1 over square root of mu tan inverse x over root mu if mu is negative, right? Then it becomes logarithms and so on. So it's, of course the tan inverse function and the log function are essentially the same by analytic continuation, right? But the interpretations are very different altogether. Yeah. So it's not just the same tan inverse function. Okay, let us look at a map exhibiting intermittency. Let us call it the cusp map. Okay. Again this is a map of an interval, this time say for convenience I will take it from -1 to 1, and it looks like this: xn plus 1 equal to f of x sub n equal to 1 minus twice square root of modulus xn, and x naught is an element of mine. Yeah. between mu equal to 3 to 4 the logistic map has regions or values of mu where intermittency is displayed once again, but the intermittency is not in the map function itself, that does not have a slope, but you will easily recognize that iterates of this could have this behavior. So again a digression, the logistic map itself perhaps look like this at a value mu less than 4 for instance. Okay. On the other hand, the iterates of the map would start looking like this. So there are plenty of opportunity for regions like this to be set up. There is plenty of opportunity for regions of that kind to be set up, which could then lead to intermittency, because it is not just the map function that determines the dynamics but all its iterates as well. So that is why the map does exhibit intermittency in between, not at 4 though, at 4 it is fully developed chaos, it is not intermittent. Pardon me?
1 plus root 8 to 4 also is.
Between 1 plus root 8 not quite up to 4, 1 plus root 8 to another value numerically determinable, the map has stable period 3 cycles, has a stable period 3 cycle. So this is actually periodic, it is not intermittent, it is actually periodic, it is not chaotic in that region at all. So the chaos disappears and then it comes back. Okay. So now you could ask, how does this happen? We will do a little more, we will talk about it numerically. Let me show you the exact bifurcation diagram for the logistic map eventually. This has been well studied. What happens is at certain parameter values there could be collisions between the chaotic attractor and unstable fixed points, and these could lead to things called crises. So there could be different kinds of crises, there are boundary crises, there are interior crises and so on, and they could lead to sudden changes in the nature of the attractor, and that is what happens in the logistic map. So yeah.
Period 3 cycles are exist from 1 plus root 8 to some k less than
to some k, yeah, less than 4, yeah.
Isn't that fully developed chaos at k itself?
Yes, there is. When I say fully developed chaos, what I mean is the following: the entire unit interval is the attractor. Now that is not true unless mu is equal to 4, because it is not an onto map unless mu is 4. It does not fill up, it does not map the unit interval to the full unit interval, but rather to a point which is less than that. Something like mu over 4, it maps it from 0 to mu over 4, and unless mu is 1 you do not hit the full interval. Okay. So let us look at this map and see what happens. Yeah, there is another question. Pardon me?
Just one clarification
Yeah.
for intermittency.
Yeah.
This means the system gets stuck in some regions for a really long time.
Yes.
That's it.
Yeah, the system gets stuck. So the stickiness, if you like, there are many dynamical systems of this kind, including some Hamiltonian systems, where you do not quite have this kind of phenomenon, but you have stickiness of some kind, and we will talk a little bit about that too. Yeah. And here you see the mechanism by which it gets stuck, as you can see, and it is a very, I mean when mu is small you could see it really could get stuck for very long periods of time, but there is no doubt that it will escape eventually, and then the system becomes chaotic again. Okay. So it is laminar bursts occur in chaotic bursts occur in the middle of laminar regions and vice versa. So that is really what intermittency is. So let us look at this map. This will fix many such ideas of intermittency clearly. It is a map which is solvable, where you can actually write down solutions and so on explicitly in the following sense. So let us first draw it, and let me draw it here and then I come back there. This map is from -1 to 1, so let us draw a little square here from -1, -1, 1 and 1 here, and this is f of x, or if you like xn plus 1. As a function of x sub n, and that is the origin. Okay. Now this is the bisector once again, and it is clear from here that this is equal to 1 minus twice square root of minus xn for xn negative, and it is equal to 1 minus twice square root of xn for xn positive. Okay. And the slope at any point, if I differentiate this and compute this, f prime of x is equal to minus 2 over twice square root of minus x and then a minus 1 again. So this is equal to 1 over square root of minus x for x less than 0, and for x greater than 0 it is 1 over f prime of x equal to minus 1 over square root of x, x greater than 0. So the slope diverges at the origin from both sides, there is a sort of cusp there, and the slope at x equal to minus 1 is plus 1 and x equal to plus 1 is minus 1. So it is immediately evident that this graph goes like this. There is an infinite out at that point, and then it is symmetric and falls back there in this fashion. And this slope here is exactly 1, and for any point x greater than minus 1 it increases. So this is the region of the marginal fixed point where you could get stuck for a long period of time, and in fact what would happen is that you do this staircase thing here and eventually go up, you go there and then you get re-injected and so on and so forth. So this map, oh by the way, the fixed point here is unstable, the slope is greater than 1, it is easy to check. Now what would the iterates of this map look like? Yeah, they'd be even more steep than this. For example, the first iterate would look like this, go up like this and come back. The slope here would always remain 1 for those maps, so there would always be this marginal fixed point, but then you have unstable periodic points, and all the periodic points are unstable and the map is actually chaotic. But you have the effect of this marginally unstable fixed point here, and therefore you have the phenomenon of intermittency in this case. We could write the Frobenius-Perron equation down for this, so let us do that. We need to be able to solve this guy, write down the two roots and then compute what the invariant measure is. Would you like me to do that, or do I take it that you will do it? Yeah, you can actually write, all you have to do is to write the Frobenius-Perron equation, minus 1 to 1 dy. So let us write this as minus 1 to 0 delta of x minus f of y, but f of y for y negative is x minus 1 plus twice minus y in this fashion, rho of y plus integral 0 to 1 dy delta of x minus 1 plus 2 root y rho of y. Now you have to convert this to delta functions in y, find the slope of the functions at that point, divide by the magnitude of the slope, and you get a functional equation for rho of x. So this is equal to some functional equation which is fairly complicated on this side, and the question is, does this equation have a solution or not? It is non-trivial, again the functional equation, but this solution has been found, and the exact answer in this case in the normalized distribution is 1 minus x over 2, which is quite remarkable because it is an explicit function of x, it is a linear function of x, looks quite simple. And if you sketch this function, since rho of x must be non-negative, so let us plot rho of x here versus x, it runs from minus 1 to 1, and at minus 1 it is equal to 1, and at 1 it is equal to 0, so it is simply a linear function of this kind. So this is a half and this is 1. That is what the invariant measure looks like. Now in heuristic terms, in crude terms, why do you think the map is symmetric about the origin, but why do you think the invariant density is piled up on the left rather than on the right, rather than being spread out uniformly?
There is more of stable region.
Yeah, there is sort of this thing here is doing it. This marginal fixed point, it is unstable, it is marginally unstable, but because of this intermittency, because of the fact that the system spends long periods of time here, remember ergodicity, the measure in any region is proportional to the fraction of the time a typical trajectory spends in that region, and it is clear that a typical trajectory, a chaotic trajectory, would spend a lot of time here. So that is reflected in this fact here. But unlike the logistic map, where you actually had unbounded invariant density and very little at the middle, here it is not like that, it is actually quite bounded, it is linear, it goes down in this fashion, okay, and the area under the curve is 1. I might add that this stickiness is actually sufficient to prevent you from having an invariant density of this kind. In fact, you would have just a delta function here, things would get stuck here, the only normalizable solution would be a delta function here, unless you had this infinity here. For reasons I will not go into here, you need to have some point in the map other than the fixed point where the slope actually becomes infinite, infinitely sharp. Then under suitable conditions you can have an invariant measure of this kind. So what I would like you to appreciate, although I am not proving this, is that the behavior here and the behavior here are related to each other. You need to have, yeah.
Suppose I cut off the top.
Yeah, suppose you do, suppose, or you, instead of cutting it off, suppose you did something like this, suppose you came along like this and did this, or something like that. So it's an, then it's not an onto map. I'd like to have an onto map. I'd like to have -1 to 1 mapped onto -1 to 1.
That's okay. I need not have an onto map for intermittency.
No, not at all. You don't need to have it.
So
Yeah.
I'll just cut it off.
Oh yes.
Change the shape of the curve.
Yeah. Okay.
I'll just cut it off.
Okay.
You still mean to say that the intermittency of the
Yes. Yes. You need not have an invariant measure of this kind. You need to have an invariant measure. For example, if you took a map like this, then there is no guarantee that you have a map an invariant measure of this kind. You could just end up with a delta function here and nothing more.
the time period that will also change.
Yeah, yeah, the behavior will change, the invariant measure will change. There is no normalizable solution which is non-negative of this kind at all. You could just have a Dirac measure here, you could just have a delta function here and the system gets stuck, okay. Because what would happen in that case is that instead of chaos, the map's Lyapunov exponent would drop to 0, because the effect of this stickiness is so strong, it prevents the chaos from happening. It actually makes the Lyapunov exponent 0, and you need to have some place here with infinite slope, unbounded slope, in order for it to actually be chaotic.
So what do you mean you can't find the invariant measure? You can just run an experiment and you can find it numerically.
Yes, they may not, yeah. So the statement is there is no normalizable invariant measure which would do this. There is no normalizable invariant measure. You need this thing to be normalizable, this density to be normalizable. It shouldn't get singular. Suppose for argument's sake the density went like 1 over x plus 1. What would happen then? You can't normalize that, you can't integrate from -1 upwards, because it is not an integrable singularity at all. So this can happen.
The time period depends
Yeah.
on the curve shape, right?
Yeah.
So why cutting off at the very top?
Because you cannot decouple the two, because anything that comes here is bound to also go there sooner or later.
But I am only interested in the time which it takes.
Does not matter. Now we are talking about what happens about re-injection, we are talking about the entire dynamics, not a single passage. We are talking about it has to, once it gets re-injected here, then that differential approximation I made would be a reasonably good approximation, provided it gets re-injected in a finite amount of time, right. So it is the map is actually exploring the entire phase space. It is not that trajectories are just exploring the neighborhood of this, in which case the behavior is trivially determinable, but you need to know what is happening everywhere else. What sort of collection region do you have, what sort of re-injection do you have, and so on. All of them play a role. And the statement I am making is that in order to have a normalizable density like this, you need to have, and I am not proving this statement, you need to have something which has an infinite slope. The slope has to become unbounded at some other point. Okay. I urge you to verify that this is indeed a solution to this equation. You have to first convert it to a functional equation and then verify that this is a solution. And as I said, if you have a non-negative normalizable solution, you are guaranteed by certain theorems that the solution is unique. Okay. Now where does that get us? We need to know what kind of, we have the invariant measure, we need to know whether it's chaotic or not. So the first thing we do is to find out what the Lyapunov exponent is. So let us do that for this map. So the lambda for this map is integral -1 to 1 dx 1 minus x over 2 times log of the slope of f prime of x, the modulus of that, and that is equal to log of 1 over the square root of modulus x, because the slope was 1 over square root of minus x for x negative and minus 1 over root x for x positive. In either case, if I took the modulus, it is just this number here. So it is mod x to the minus half modulus x in this fashion. And of course it is an even function and that is an odd function, so that portion goes away and you are left with just an integral half log mod x. It is easy to do and I urge you to do this, and the answer will turn out to be a half. Okay. Notice this is negative in the region of integration, so that cancels the minus sign and you end up with a half. So this is certainly greater than 0, implies chaos, but it is intermittent chaos. In fact, finding this invariant measure, invariant density numerically is non-trivial. You do this by taking a long time series and drawing a histogram, and this thing takes a long time to build up here. So you really have to run for a very long time. You have to run a trajectory and you have to leave out the initial transients which would be specific to given initial conditions, and then eventually you end up with this. But this is an analytic solution. You can easily check that this is an exact solution to this problem here. Okay, so we have a chaotic map. With a chaotic map you still have intermittent behavior, and this is exactly solvable. So it is like a paradigm, it is like a model, like the logistic map. Now of course you could make this uniform, you could make this density uniform without changing any other properties of this map by taking this portion of it and doing exactly what we did for the Bernoulli shift instead of the tent map. In other words, do this in this fashion. So this map function would be f of x equal to 1 minus twice root minus x for x negative, but it would be twice root x minus 1 for x positive. And that is sufficient to make all the difference, because now you have a marginal fixed point here and you have a marginal fixed point here too, and they compete with each other. So you do not have any right to expect an invariant density of that kind. You can write down the functional equation once again, and I urge you to do this for this map and verify that in fact the invariant density is a constant. So for this new map the invariant density is simply this. So the area under the curve is again 1 and it is just a constant. So rho of x is just equal to a half for this anti-symmetric map. The earlier map was symmetric, but the invariant density was not symmetric. On the other hand, here the map is anti-symmetric, but the invariant density is symmetric. In the logistic map and the tent map at parameter value 2 with slope 2, the map function was symmetric about the midpoint and the invariant density was also symmetric.
So this doesn't have any intermittency.
This doesn't, pardon me?
This doesn't have any.
Yeah, it will have intermittency. Why not?
Right.
Why not?
If it has intermittency, then the rho should be greater than, right, because it spends more time.
No, not necessarily true, not necessarily true, because what has happened in a crude sense is that these regions have kind of overlapped in this case. So once again it is easier to handle than the other map simply because the invariant density, so I do not have to weight it with any function of x, everything is uniform here.
But the long burst, I didn't get
yeah.
it. The long bursts of periodic Fermi, that's
Yeah.
what you gave us the
Yeah,
definition.
yeah.
So there is no longer a long burst because it's traveling over the region with equal ease.
But the way it jumps from point to point is not necessarily periodic, whereas here once you are here, I am drawing this in an exaggerated way, but once you are here there is a long staircase behavior, that behavior is lost in this middle region, and again out here there is a long staircase behavior which is lost in the intermediate region. So definitely it would look very periodic, but not with a constant amplitude, slowly increasing maybe or something like that when you are in these regions. So that is what intermittency is. It is not as if it is strictly periodic, any function which is monochromatic or periodic would just go on forever, minus infinity to infinity. So the periodicity stops definitely, and if you look at it with infinite accuracy, certainly it is not periodic, there is no single period discernible.
Even though it is chaotic,
yeah.
In the middle region, say
Yeah.
from minus 0.25
Yeah,
to plus
yeah,
0.25,
yeah.
there also it will be stuck for a reasonable amount of time.
Yeah,
Though
for the
in
same
a-
oh
in a
yes,
completely
yes,
random sense.
I agree because of this, yeah. Once you have a density, then the time, the fraction of the time t over a long trajectory, the fraction of the time that it spends in any interval is in fact proportional to a to b rho of x dx for a normalized invariant density. So this is certainly true, this is a fraction. So if you took a long orbit and you asked how much of the time does it spend in any given region, that is measured directly by the integral of the invariant density, the measure of that region, it is measured, it is given directly by that is certainly true. So this map has interesting properties, so does the other one, but the other one has this extra feature that the map is symmetric, whereas this one does not. Now you could ask, why did I choose something which went like x plus perhaps x squared here. If you expand the map near x equal to -1, the map function would have a leading term like x plus 1 and a term which goes like x plus 1 whole squared and so on and so forth. So let us see if we can generalize that a little bit, and let me shift it to the origin. So let us suppose your intermittent maps are like this here, and this map function f of x near the origin is like x, that is the leading term, plus something or the other, so plus some constant maybe multiplied by x to the power alpha. Now let us take out an x into 1 plus this thing here. This is typically what would happen near the origin. Now alpha, if it is a constant, if alpha is 0 first of all, then nothing interesting happens, it just is a map which is going to look like this straight away, linear with a slope greater than 1 because its slope is 1 plus c. But if alpha is not 0 but a positive number, generically if you have a function which is expandable smoothly around this point, alpha would start with 1 and then higher powers go on, like in the case of these maps. This map can be written in the neighborhood of this point as x plus 1 plus a term which is x plus 1 whole squared and so on in this neighborhood. But in principle you could have an alpha which is positive, does not have to be 1, could be greater than 1, could be even less than 1 here. So the degree of stickiness out here, as you can see, is measured directly by alpha, okay. And for such maps you can actually plot the Lyapunov exponent as a function of the parameter alpha, and it turns out that if you plotted lambda versus alpha, then if you start at some point like that, which is certainly positive, because if alpha is 0, this is a map with slope 1 plus c, and this is unstable, and the assumption is the map is chaotic by its behavior elsewhere. So it starts with some Lyapunov exponent, and as alpha increases it is getting more and more sticky here, and therefore the Lyapunov exponent actually drops in this fashion, and it turns out at alpha equal to 1 it drops to 0 and the map is no longer chaotic. So some kind of phase transition takes place. On the other hand, we also know that in the cusp map, for example, there is a Lyapunov exponent which is non-zero, which is positive, and that happens because of the infinite slope elsewhere. So you actually get rid of this stickiness of this point by having a sharp spike somewhere else in the map. So they do not fall in this class of maps, these maps do not fall within the purview of this general statement here. Okay, this is a technical aside, I don't want to get too deep into this, but let me go back. You could also ask, can I construct maps of this kind? Can I construct a map where, for example, I have not a square root cusp up there and a square root behavior, the map function which had square root of x and so on. What about x to the power 1/3 or x to any other power, cube roots and so on? The answer is yes, you can construct whole families of these maps, and whatever exponent alpha you have here, you need to have a 1 over alpha type behavior in the slope up there roughly. You need to have something which becomes unbounded, and therefore the nature of this stickiness here can be related to the nature of the cusp elsewhere to get a finite point. In fact, you could construct an infinite family of such maps for which you have invariant densities which are all sorts of prescribed functions of x, not necessarily linear functions. This is the inverse Frobenius-Perron problem. If you give me a smooth function as an invariant density, can I construct a map of which this is the invariant density? Now that problem can be solved modulo certain qualifications, and it turns out for a huge variety of such functions rho of x, you can actually find, you can tailor make a map whose invariant density the given function would be. So that is actually turns out to be a not too difficult problem. Yeah.
Density with respect to space.
Yeah.
You know the distribution with respect to time as well, right?
Yes, because of ergodicity.
You can
Yeah.
find out the function.
Pardon me?
That means you can find out the function because
I can find the map function.
Actually,
Yeah, I can find the map function. Yeah, it's a non-trivial problem, but it's doable. Yeah. After all, the Frobenius-Perron equation is an eigenvalue problem. So in some sense, you are saying you're giving me the eigenvector, and now you go back and construct the kernel. This is.
Can I say that this is possible only the system's algorithm?
Yes, the whole thing is true only for certain classes of chaotic systems, absolutely, and in one dimensional maps. So things are restricted to one dimension, very much so. I don't know how these things, I don't offhand have direct statement about how this generalizes to higher dimensions, I am not too sure. Yeah. So for one dimensional maps a great deal is known, much is known about these chaotic maps. Yeah, the whole thing is we are dealing only with chaotic systems now. Okay. Let me go on to, we will come back a little bit later to understanding what coarse graining in phase space is and so on, but let me go on to a two-dimensional map. Such maps exist too, and let me give you in particular an example of a very simple two-dimensional map which is invertible and yet exhibits chaos, and this is in fact a model which is used as a model for Hamiltonian systems, where, as you know, things are conservative. So we will look at an area preserving map where you have chaotic behavior, unlike the case of the Bernoulli map or the logistic map and so on. They do not model conservative systems, but now we are going to talk about a map which models a conservative system and yet exhibits chaos, and the map is the following. It is called the Baker's transformation or the Baker's map, because it is supposed to mimic the way in which bakers make bread from dough. The baker is not a proper name, it is a common noun, and it is supposed to model the way bakers make dough, which is to take the dough, to stretch it and fold it back, and they keep folding it back, and this mixing is what is producing chaotic behavior eventually. We saw in the Bernoulli shift or the tent map, you stretched and you folded, you stretched and you folded in one dimension. Now let us do this in two dimensions. So the map looks like this. You have two variables, xn and yn at time n, and each of them runs between 0 and 1, and the map function looks like this. So here is xn, here is yn 0 to 1, and you take this square and do the following manipulation on it. Stretch this square by a factor of 2 in the x direction and compress it simultaneously in the y direction by a factor of 2. So at the next stage this becomes like this. So this is x and that is y, and this is 0, 1, this is 2, and that is a half. And then cut this piece exactly as you did in the Bernoulli shift and put it on top here. So this goes off into this, and this is xn plus 1, yn plus 1. So just to see what we have done, let us do the following. Let us take this map and shade this region, the other half. So I keep track of where it is gone, and when I extend it, that shaded region has come here. And now I cut and put it back, and that shaded region has gone there. Every point on the square has been mapped onto some other point on the square, but this is the transformation. What is the actual function? And it is also clear the area has been preserved. You have not done anything at all. You have stretched this side by a factor of 2, but you have also compressed the other one by a factor of 2, and you put the square back onto the square, but you have mixed up things here. So a point here will go somewhere else, a point there will go somewhere else, and so on in this map. And what does the map function look like? Well, it says xn plus 1 equal to 2xn modulo 1. Right, because you are going to stretch and then you are going to put things back. Yn plus 1 is equal to half yn, you brought it down, provided xn was between 0 and a half, otherwise you added a half to it. So you compressed it, but then you cut and pasted it back. So you actually added a half to it, right? So this was equal to this, so provided xn is less than a half, but it was equal to half plus half yn, xn was greater than a half, and the whole thing is modulo 1, everything is modulo 1. The map is invertible. It is definitely invertible, because I can tell you precisely where each point came from. There is no 2 to 1 business here. Every point has a unique pre-image. If I started at some point here, I stretched, so it went to double this, and it came to half its height on this point here. If I started at some point here, then when I stretched, it came down somewhere here. And then I cut it and put it back, so it went up somewhere here. So certainly you can identify the pre-image of every point, and the area is preserved. So it mimics a conservative system. On the other hand, there are two Lyapunov exponents, one corresponding to the stretching or contracting in the x direction and the other in the y direction. So you have two Lyapunov exponents, and let us call them lambda sub x and lambda sub y, and these are easy to write down by inspection. What would these be? What would be the stretch factor in the x direction? It is the original Bernoulli shift, so this is log 2. And what would lambda y be? Log a half, absolutely right. And it is clear that the area must remain the same, because after all, under this map what is happening is that dx dy is going to dx prime dy prime, this is the area element if you like, and this is supposed to go like any area element expands. So it goes like e to the power lambda x plus lambda y t dx dy. That is the whole point about the Lyapunov exponent, and it does not change, so this cancels that. So the map is area preserving. But it is definitely chaotic, you are definitely losing information, because what happens to the next iterate of this? I iterate once more and I do the same thing, then it is not hard to see that you are going to have something like this. This region is going to get scrambled up a bit, it is going to look like this. You increase it a little more, it is going to get even more striated and so on. So you are going to have if you take a cross section here, you are going to have a sort of fractal structure, this whole thing. So you are certainly mixing up the entire thing. So this pulling and cutting and putting it back, and cutting and putting it back is like a Baker's transformation. And the fact that it has one positive Lyapunov exponent is enough to show that it has chaos in this. But now I pointed out that this map, and I will stop with this, that this map is invertible. So you should really be able to recover, you are not losing any information in the sense that you should be able to say where you came from. Is that really true or not? We saw in the Bernoulli shift, the way to understand the shift was to write x naught as 0.a0, a1, a2, etc. In which case you ended up with x1 is 0.a1, a2, a3 dot dot dot, because you multiplied by 2 and threw away the integer part, which means you got rid of the knowledge of a0. What would you do for the Baker transformation? One of those goes to the y coordinate. So there is a clever way of doing this, and I will stop with this, and the clever way is to say, suppose x naught is this and suppose y naught, the initial is 0.b0, b1, b2 dot dot dot, then write the pair x naught y naught in the following strange way. So put a dot here and write a0, a1, a2, and write this guy backwards, b0, b1, b2 in this fashion. Represent the pair x naught y naught by this strange number, and then in the next shift all it does is precisely what it did earlier. So you have b2, b1, b0, a0 dot a1, a2, a3. So if this is x naught y naught is represented by this, then x1 y1 is represented by this. That half which was sitting here has moved over to this side. So you haven't lost anything. In other words, you can tell precisely where you came from. So this in fact establishes that the map is invertible. You are not losing anything at all, and yet you have chaos. So it is important to remember that chaos does not imply always shrinkage of volume and loss of information. You still have exponential sensitivity to initial conditions, but yet you could have something which is invertible in this sense, completely solvable if you like, and still display exponential sensitivity. So I stop here this time, and then we will take up some other aspects such as coarse graining next time.